Okay, so now we get a new formula, and the notation's going to be a little different and a little weird. The general multiplication rule. For a chance process, the probability that events A and B... Sorry, I'm a little out of breath. Just carried Leo down the stairs. He's still not feeling good. Needed to get him outside. He's a big, heavy dog. Anyway, the probability that events A and B both occur is found with the following formula. Probability of A and B. Now you have a formula for or B. Actually, you have two of them. Here's the probability of A and B. It's the probability of A times the probability of B given that you know A happened. That's what that notation means. Given that you know A happened. If A happening can affect the probability of B happening, then we can't just have the probability of B here. We have to sort of clear out the fact that A happened. Like, think about it. If I pick two people from your class to just give an A for the semester, once I pick the first person, let's say that's not you, then isn't the probability that you get picked different, right? It's one less person to choose from, so it's different. Okay, where probability of B with A, with this little vertical line segment in it, is the probability that B happens given that A happened. It's a condition. This is called a conditional probability right here because I'm giving you some kind of condition. You know something happened. So how do the odds change? So I'm going to go to page 295. Excuse me. And let's look at do teenagers post. Here we go. The Pew, that's an actual thing. The Pew Internet and American Life Project, that's a nonprofit company that does statistics, found that 93% of teenagers use the internet, and 55% of online teens, look at that right there, of online teens. That's not just teens, that's a condition. If I know that they're online, 55% of them have posted a profile on a social networking site. Okay, that percentage is much bigger now. Anyway, find the probability that a randomly selected teen uses the internet and has posted a profile. Show your work. And has posted a profile. Okay, the most important part of doing problems like this is recognizing what I pointed out. It said 55% of online teens. See, that's a real subtle phrase that's giving you a condition. Hey, if they're people who are actually online, this percent applies to them. It's not 55% of all teenagers. It's 55% of those who are online, have posted a profile. That means probability that they post given that they are online. Okay? Definition. Notice that probability of A and B is equal to the probability of A times the probability of B given A. I already wrote that up at the top. I'm repeating myself. And you simply divide both sides. See, I'm gonna do a little algebra and write another formula from that one. If you divide both sides by probability of A, you actually get a probability condition. Like if you get this one and divide, you're gonna have this by itself. So you're gonna have a conditional probability formula. Probability of B given A. The conditional probability of B given A is equal to, if I divide, that's going to be on the bottom and that's going to be on the top. It's a fraction, and it goes the probability of A and B divided by the probability of A. Just a little simple algebra trick from our original multiplication formula. So those are two different formulas. One for A and B, one for the conditional probability B given A, but I got them from the same spot. Okay, here we go, the tree diagram. Your third organizational chart. After the two-way table and the Venn diagram, your third organizational chart that we'll use to find probabilities is the mighty tree diagram. When are we going to use this? When we're given stuff that's a conditional probability. That thing about Democrats and Republicans and men and female, there was no conditional probability there until we were asked one. The information we were given was all about men, all about Republicans, and then men who are Republicans. It wasn't about if I know you're a Republican, here's the probability that you're a man. We didn't get that kind of thing. We were asked it, but we weren't given it. If you're given conditional probabilities, you do a tree diagram. Here's an example. Shannon hits the snooze button on her alarm 60% of school days. I guarantee you I'm 100% of school days with the snooze. If she hits snooze, there is a 0.7 probability that she'll make it to her first class on time. Now, look, if she hits snooze, well, we got a 60% chance of hitting snooze. If she hits snooze, that makes this a conditional probability, just like if they're online. If she doesn't hit snooze, there's another one, and gets up, there's a 90% chance that she'll be on time if she doesn't hit the snooze button. Okay, here's a tree diagram that organizes that information. I'm going to write this in first. Notice if she snoozes, that goes like this. The probability of on time given snooze. If she snoozes 0.7, that's a conditional probability. That 0.7 is that right there. If she doesn't snooze, find the probability she doesn't snooze and she's late. Okay, so we're going to deal with that after I do the tree diagram. Here we go. From the beginning of this problem, there are only two possibilities: a snooze and no snooze. And I was given both of those probabilities in this paragraph. Ready? The probability she snoozes is 60%. Now, they didn't give me the other number, but you can tell what the other number is real quick because you know the complement formula. If the probability that she snoozes is 60, the probability that she doesn't snooze is 100% minus 60%. It's 40%. Okay, now here's the thing that happens after that. Conditionally, if she snoozes, there's a probability that she is on time. There's a probability that she's late. Now, if she doesn't snooze, there's a probability that she's on time, and there's a probability that she's late. I need you guys to know, though, these are straight up probabilities. Snooze or don't snooze. These are conditional probabilities. On time on the condition that she hit the snooze button versus on time on the condition that she didn't. That's different from the Republicans and men, the information we were given. Okay, here we go. If she hits snooze, there's a 70% chance that she'll make it. So if she hits snooze on time is a 70% chance. We know this one has to be 30%. These have to add up to 100, just like these had to add up to 100. Now, if she doesn't hit snooze, there's a 90% chance that she's on time. That means there's a 10% chance that she's not. That's your tree diagram. And how you find probabilities go like this. That's the probability of snooze. This, like this, that's the probability of on time given that she snoozes. But if you want the probability that she snoozes and she's on time, you go probability that she snoozes times the probability that she's on time given that she snoozes. So to get this A and B, there's the snooze, probability of A. There's the conditional probability. You multiply these two together to get the and probability. You guys see it? 0.6 times 0.7, 0.042, I think. Is that how that goes? Okay, so the probability she didn't snooze and she's late. I'm supposed to find the probability that she didn't snooze and she's late. No snooze and late. Didn't snooze and late. So here's an and probability. So I'm going to follow this formula. I got to find the probability of no snooze. Sorry, I'm writing that really small. And then I go times the probability that she's late, but given that she didn't snooze. I'm writing right into my tree diagram. Sorry about that. That's going to go no snooze 0.40. Probability that she's late given that she didn't snooze 0.10. When I multiply that together, I get 0.36. The probability that she doesn't snooze and is late is 0.36. Okay? If I ask what's the probability she snoozes and is late? Snoozes and is late. Snooze and late would be snooze times late given that she snoozed. Snooze, late given that she snoozed, it would be 0.6 times 0.3. All right, next page.